There are many reasons you might want to know how many microbes you have in a particular sample. That sample could be a culture that you grew in the lab, or it might be something that you got from the environment, such as a sample of water. But looking at any of these samples or cultures, it's impossible to tell just by looking with your eyes how many microbes are present. And so one technique that can be used to estimate how many microbes are present is serial dilution. In serial dilution, you'll take a sample from your sample and dilute that, and then take your dilutions and plate them onto agar plates. And some of those dilutions should be dilute enough that you only get single colonies on your plate that are countable. And then you can use those plates to back calculate based on the amount they were diluted to estimate the original number of microbes in the sample. So let me show you how it works. You'll need tubes that have 9 milliliters of liquid in them. Typically this is water. And so your first dilution, you'll take 1 milliliter of your sample and add it to the 9 milliliters of water, and this will give you a total volume of 10 milliliters. And so your dilution is 1 milliliter into 10. And this is a dilution of 1 in 10. Or it also can be written as 10 to the minus 1. And then you do another tube. And so this was a 1 in 10 dilution from this tube, but we're always going to relate back to the original sample. And so what you can do is multiply these dilutions. This one was 1 in 10, and this is going to be times another 1 in 10, so this would be a 1 in 100 dilution, or 10 to the minus 2. And we'll continue in this way. For this example, I'll show 4 dilutions. All right, so this was another 1 in 10 dilution. So again, we multiply. This is going to be 1 in 1,000, or 10 to the minus 3. So you notice as we go along, for each of these, I'm just adding another 0 because we're multiplying by another 1 in 10 dilution, or I'm adding another number here to our dilution factor. So then now that we have our serial dilution set up, next is to do the plating onto agar plates. And so what we'll do is we'll take a small volume from each of these and plate onto an agar plate. If your sample is dilute enough, you might actually plate the original sample. So you would take typically around 100 microliters is a good amount to plate. This is the same as 0.1 milliliters onto your agar plate. And we'll do this for each of the dilutions as well. And then you look and see how much growth is there on each plate. Let's say that the sample was actually quite concentrated, then you might get just a whole lawn of growth here. And maybe it's still a lot of colonies here, so many that it's really hard to count. And same thing for this plate, still just too much growth. You can't make out single colonies very well. So all of these we would label as too numerous to count, TNTC. But now when we get to this dilution, the 10 to the minus 3 dilution, now we're starting to be able to see distinct colonies that are countable. Let's say we have 110 colonies here, and only 1 colony here. So the most countable plate is going to be this one right here. So this is the one we're going to choose to use for our calculation to determine how many bacteria or how many microbes are actually in the original sample. And generally, a good rule of thumb is that somewhere between 20 to 300 colonies is a good number. 110 colonies on a plate is very countable. Now I'm going to show you how to back calculate how many microbes were in the original sample. When we were counting colonies before, here on the agar plate, really what we're counting are colony forming units. Most of these are probably only a single cell that is growing into a colony, but it's possible there could have been 2 cells or 3 cells here that formed the colony unit. And so we refer to these as colony forming units. And the formula for calculating colony forming units in the original sample is number of colonies, or number of colony forming units on the plate, divided by the dilution times the volume plated. In our case, there were 110 CFUs on the plate that we're using for our calculation. The dilution factor is 10 to the minus 3, and the volume plated was this 0.1 milliliters. That's how much of each of these we put onto the plate. At this point, you could just plug this into a calculator and get the answer back, or you can work the math out in your mind. And so 10 to the minus 1 times 10 to the minus 3 is 10 to the minus 4. And then whenever you have a negative exponent on the bottom of a fraction, this is the same as multiplying by the same number with a positive exponent. So this would look like, 10 to the positive 4. This could be rewritten as 110 times 10 to the 4 CFUs per mil. And just to put this in proper scientific notation, we would move the decimal point over until there's only 1 digit in front of the decimal point. And each time we move over, we're going to add a number to the exponent. So this moves over twice, so this will become 10 to the 6. Okay, so the answer here is the original sample would have 1.1 times 10 to the 6 CFUs per mil, which is pretty concentrated. This sample had a whole lot of microbes in it. In the Labster simulation this week, you are going to perform a serial dilution. And I just want to point out that the formula that's used in Labster is the same as the math that I do, but it's presented just a little bit differently. Number of colonies times dilution factor divided by volume plated. So this is the formula that's used in Labster. So it would be 110 colonies times the dilution factor, which is the positive version of that 10 to the minus 3 exponent. So this would be 10 to the 3, because it's been moved to the numerator in this equation, just like we did, but they do that kind of up front. And then divide by the volume plated, which is the same, 0.1 ml. And if you plug this in, you should get the same answer of 1.1 times 10 to the 6 CFUs per mil.